In this lesson, we'll be looking at the relationship between stoichiometry and the solubility product constant Ksp. We'll also look at how the solubility of a sparingly soluble salt is affected by the addition of a common ion. So a new vocabulary term to define. So we have molar solubility. And just like it sounds, it's the number of moles of a solute per liter in a saturated solution. So just going straight into the math, what is the molar solubility of a lead-2 iodide if its Ksp is 8.7 times 10 to the minus 9? First thing you want to do is you want to set up the equilibrium expression. Remember, if it says Ksp, that means that we have a solid in equilibrium with its ions. Typically, most people use S for the molar solubility, for S's for solubility, but I use X's just because when I'm trying to write this on the board, my S's always end up looking like something else altogether. But my X's are clear. And also X is what we used when we were doing the stoichiometry unit. So we know by stoichiometry that for every one lead ion, there's going to be twice as much iodide. So if your molar solubility is X, that means the concentration of the iodide is going to be 2 times X. So you write down your Ksp expression. Products over reactants, remember solids have a value of 1. Fill in the numbers. Now remember, you're going to be squaring everything inside the concentration brackets. So it's going to be 4x squared times x. A lot of students are bothered by the fact that that 2 ends up being used twice. That's just how the math works out. So we end up with 8.7 times 10 to the minus 9 is equal to 4x cubed. Divide both sides by 4 and then take the cube root. And you get that the molar solubility of lead-2 iodide is 1.3 times 10 to the minus 3 molar. So what is the molar solubility if we spike the solution with some additional iodide? Remember, potassium is one of those spectator ions. It's not going to be participating in anything. But the iodide is definitely in this equilibrium. So this time, instead of using 2x for the iodide, we know what it is. It's 0.2 molar because that's how much we added to it. So we go ahead and we write down what we know, fill in the numbers. Remember to square the iodide concentration because it has a coefficient of 2. Solve for x. And now we have a molar solubility of 2.2 times 10 to the minus 7. This is called the common ion effect. We'll come back to it. But notice as a result of adding in some more iodide into this equilibrium, we've gone from something that is on the millimolar level to 10 to the negative 7th molar. So it has changed it by a factor of 10,000, 4 orders of magnitude. All right, another expression wants to know what the Ksp of lead-2 phosphate is if it has a molar solubility of 1.5 times 10 to the minus 9 molar. So this time we're given the x, and we have to find Ksp. So we do the same thing. Write out the reaction equation. Write out your Ksp expression. So this is Ksp, so that means that our initial reactant is a solid, so it doesn't show up in the Ksp expression. So we use our stoichiometry x's. So this is going to be 3 times the molar concentration, molar solubility, and the phosphate is going to be 2 times the molar solubility. Put those concentrations in. We know what x is, but we're just kind of saving it until we get to the very end, so we don't have to work with that really small number in scientific notation too many times. So 3 cubed is 27, so you end up with, when you go 3x quantity cubed, you end up with 27x cubed. 2x quantity squared is 4x squared. Then you multiply your 27 times your 4, and multiply the x cubed times the x squared. Remember, exponents are going to add. And you end up with 108 x to the fifth. So we already know what x is, and there should be a unit of molarity on there. So we do Ksp is going to be equal to 108 times 1.5 times 10 to the minus 9, quantity, or raised to the fifth power. And we get that the Ksp for this salt is extremely small. It's 8.2 times 10 to the minus 43. So it tells you that this is heavily reactant favored. It does not make very much product at all. All right, so here we have the definition for the common ion effect. The addition of one of the ions that is participating in that equilibrium will reduce the compound's molar solubility. And we'll actually see why in the next lesson, which is on Le Chatelier's principle. So it says, what is the molar solubility of lead 2 chloride? Give you the Ksp value. So we kind of go through the steps again, write down the reaction equation, write down your Ksp expression, substitute in your stoichiometric amounts. So X is for the lead plus 2 ion concentration, and 2 times X is going to be for your chloride concentration. We do the math, solve for X, and we end up with the molar solubility of lead 2 chloride. So 0.016 molar. So yes, lead 2 chloride will form a precipitate if there's enough chloride present, but it's one of those that's kind of on the edge as far as whether it's going to make a good precipitate or not. So the next part, we're going to use the common ion effect. What is the molar solubility of lead 2 chloride if we spike it with some chloride, 0.2 molar chloride? Remember, sodium is a spectator. So we still have the same Ksp expression, but now we know that chloride is not 2x, it is 0.2. And we're going to solve for x, and again, we see that we have a significant decrease in the molar solubility. So this one is on the order of 10 to the minus 2 moles per liter for its solubility, and down here it's 100 times smaller, so 10 to the minus 4 moles per liter. All right, so that's it for our Ksp and molar solubility. Remember Ksp, it's just that little sp stands for solubility product. It describes an equilibrium between a solid and its ions in solution. It's really important that you remember that, because you're not necessarily going to be told what the reaction is in total. We saw that you can predict how soluble something is by looking at its Ksp value. So the bigger the Ksp, the more products you have, the more soluble that salt is. We also used molar solubility, did some calculations with it, just to look at what the common ion effect is and how it affects molar solubility. And common ion effect, the key thing to that is that you have to add an extra ion that is participating in that particular equilibrium. If you add a random ion, like say we're talking about lead 2 chloride and you added some bromide, that's not going to affect anything, because it's not part of that equilibrium. Actually, it started another equilibrium, but we're not going to worry about that. All right, so that's it for this particular lesson. Thanks for listening.